Welcome to The Explainer. Today, we are going on an incredible journey. A journey right into the very heart of matter to really understand the atom. It's a story packed with brilliant minds and totally radical ideas that, honestly, reveal a reality that's way stranger and more wonderful than you could possibly imagine.
So let's just start with a really simple question. What are you really made of? I mean, deep down. We all know the answer is atoms, right? But what is an atom? To really get to the bottom of that, we have to kind of shrink ourselves down and follow this amazing story. From thinking atoms were just solid little balls to seeing them as these weird, fuzzy clouds of pure probability.
So, here's our game plan. We're going to start with the very first ideas about the atom, and then we'll see how a really beautiful, elegant model ran into a huge, fatal problem. After that, we'll witness the quantum revolution that just completely rewrote all the rules. And finally, we'll see how atoms are actually built. It's basically a scientific detective story. Let's get into it.
Okay, our story really kicks off back in the 19th century. And for the longest time, scientists were just trying to get a handle on the most basic picture of what an atom could even look like.
It all began with John Dalton's billiard ball model. He imagined atoms as these tiny, indestructible little spheres. Simple enough. But then that idea got a major shakeup when J.J. Thomson discovered the electron. This led to his plum pudding model. Picture a positively charged blob with negative electrons just kind of stuck in it. This discovery that atoms had parts really set the stage for one of the most important experiments in the history of physics.
So along comes Ernest Rutherford, and what he does is he fires these tiny positively charged things, they're called alpha particles, at a super thin sheet of gold foil. Now, most of them went straight through, as expected. But, and this was a huge shock, some of them bounced right back. That result was just mind-blowing. It meant that all the positive charge in an atom wasn't spread out. It was all concentrated in this tiny, dense center that he decided to call the nucleus.
And that led us to the planetary model. You've probably seen it. It's got a tiny, dense nucleus right at the center, with electrons orbiting it just like planets going around the sun. This was a massive leap forward. For the first time, it showed us that an atom is almost entirely empty space.
But as beautiful and as elegant as this little solar system model was, it had a giant problem, a really big one. According to the laws of physics that everyone knew and trusted at the time, this atom shouldn't be able to exist for more than a tiny fraction of a second.
Okay, so here's the fatal flaw. According to classical physics, an electron circling a nucleus is constantly changing direction, which means it's accelerating. And an accelerating charge has to give off energy. It has to radiate it away. So that poor little electron should lose speed and just spiral right into the nucleus in a split second. Poof! The atom collapses. But obviously they don't. Atoms are incredibly stable. So either the model was wrong or physics itself was wrong.
The hero who stepped in to save the atom was a Danish physicist named Niels Bohr. And his solution was, well, it was radical. He basically decided to just change the rules of physics.
Bohr's big, crazy idea was this: what if electrons are restricted to specific, fixed orbits? He called them energy levels. Think about it like a staircase. An electron can be on step 1 or step 2, but it can never be floating in between the steps. And it could jump between these levels, but only by absorbing or emitting a very precise amount of energy. This was the first quantum leap for our understanding of the atom.
And the thing is, it worked. Brilliantly, in fact. For hydrogen, which only has one electron, Bohr's model perfectly predicted its behavior. But the moment you tried to apply it to any other atom, one with multiple electrons, the whole model just fell apart. It couldn't handle all the complex interactions between them. So it was a crucial stepping stone, for sure, but it wasn't the final answer. The rules, it turned out, needed to get even stranger.
And that brings us to where we are today, to our modern understanding. We're now leaving behind those nice, simple orbits, and we're stepping into the truly bizarre, totally counterintuitive world of quantum mechanics.
So the huge shift in thinking was this: tiny things, like electrons, they don't act like little billiard balls at all. They have this crazy dual nature. Sometimes they act like a particle, and sometimes they act like a wave. And what that means is you can't actually know an electron's precise position and its exact momentum at the same time. This is the famous Heisenberg uncertainty principle, and it just completely demolishes that old idea of a neat, predictable orbit.
So if electrons aren't in orbits, where in the world are they? Well, the answer comes from Erwin Schrödinger and his famous equation. And the solutions to this equation are profound. They give us something called a wave function, which doesn't tell you where the electron is. Instead, it defines a 3D region of space where the electron is likely to be found. So we trade orbits for these fuzzy probability clouds, and we call them orbitals. Now, to describe these orbitals, physicists use a set of 3 quantum numbers. You can just think of them as the electron's address. The principal number, n, tells you the main energy shell. That's kind of like the city it lives in. The azimuth number, L, tells you the shape of the orbital. Think of that as the street. And the magnetic number, m, tells you its orientation in space. So, the house number. Okay, so now we've got our modern model with these quantum orbitals. But how do the electrons actually decide which orbitals to live in? Turns out, they're very strict rules, and these rules govern the entire structure of the periodic table. So this brings us to the final pieces of our puzzle. To build any atom you can think of, from hydrogen all the way to uranium, we just need to follow 2 really key principles for filling up these orbitals.
First up is the Pauli exclusion principle. What it says is that no 2 electrons in an atom can have the exact same set of quantum numbers. It's like no 2 people having the same social security number. And this is possible because there's a 4th quantum number called spin. Electrons have this built-in property, and it can either be up or down. This rule is super important because it means each orbital can hold a maximum of 2 electrons, but only if they have opposite spins.
And the second big rule is Hund's rule. Honestly, the easiest way to think of this is the bus seat rule. Imagine you get on a bus with a bunch of empty 2-person seats. You're not going to sit right next to a stranger if you don't have to, right? You take your own empty seat first. Well, electrons do the same thing. If they have multiple orbitals with the same energy, they'll occupy each one by themselves first, all with the same spin, before they're forced to double up. They just want their own space.
And when you put them together, these principles, they're everything. They're the reason the periodic table is structured exactly the way it is. They're what dictates how atoms bond with each other, how they react, and all the properties they have. These are the fundamental rules for building the matter that makes up our entire universe.
So there you have it. We've gone from these simple, indivisible spheres to a tiny little planetary system, and finally to this strange, beautiful model of probability clouds governed by these bizarre quantum rules. We have an absolutely astonishing picture of the atom now. But you know, the journey of science is never really over. So the question now is, as we keep looking deeper and deeper, what new, even stranger realities are just waiting for us to discover?